Hello students, today's topic will be on electromagnetic radiation. First of all, let us have a brief introduction. Electromagnetic radiation, EM radiation or EMR, refers to the waves or their quanta, photons, of the electromagnetic field propagating through space, carrying electromagnetic radiant energy. It is a traveling disturbance in space that comprises electric and magnetic components. Unlike the field associated with a common magnet or the Earth, the magnetic field associated with electromagnetic radiation is constantly changing its direction and strength. The electric field component undergoes exactly the same behavior. It is the interaction of the electric and magnetic components of radiation with matter that is responsible for all the phenomena that are associated with radiation, such as human vision, sunburn, radio, television, and of course spectroscopy. It includes radio waves, microwaves, infrared, visible light, ultraviolet, X-ray, and gamma radiation. Now, spectroscopy and electromagnetic radiation. Spectroscopy is the study of electromagnetic radiation and its production from or its interaction with matter. Spectroscopic techniques employ light to interact with matter and thus probe certain features of a sample to learn about its consistency or structure. Historically, spectroscopy has played an important role in the development of atomic theory, and it is extensively used for fundamental studies. Spectroscopic techniques are widely used in biochemistry laboratories for quantitative and qualitative analysis. Now, the important features of electromagnetic radiation. First, the periodicity of the disturbance or the distance between adjacent troughs or adjacent peaks is referred to as the wavelength of the radiation. The number of times the electromagnetic field undergoes a complete cycle per unit time is called the frequency. The speed with which radiation can travel is limited, and moreover, radiation of all wavelengths travel at a single speed. This is referred to as the speed of light, universally denoted by the symbol c. The speed of light and every other radiation is dependent on the substance through which it travels and reaches a maximum in a vacuum. The speed of light is a constant of proportionality between frequency and wavelength as described by the following equation. C equals nu lambda, where nu is the radiation frequency, lambda is the radiation wavelength, and c is the speed of light. The interpretation of this equation is that wavelength and frequency are related. Electromagnetic radiation of long wavelength must have a low frequency, whereas radiation of short wavelength must have a high frequency. Second, the electromagnetic spectrum consists of different size wavelengths from short, high energy radiation to long, low energy radiation. This energy is related to the frequency and wavelength of the electromagnetic spectrum. Light is just one form of energy in this spectrum. The visible region from approximately 380 to 700 nanometer is the area seen by the human eye. The shortest wavelength corresponds to the color violet and the longest to the color red. White light is a continuous spectrum of wavelengths. Third, the interaction of electromagnetic radiation with matter is a quantum phenomenon and dependent upon both the properties of the radiation and the appropriate structural parts of the samples involved. This is not surprising, since the origin of electromagnetic radiation is due to energy changes within the matter itself. The transitions which occur within the matter are quantum phenomena, and the spectra which arise from such transitions are principally predictable. Fourth, electromagnetic radiation is composed of an electric and a perpendicular magnetic vector, each one oscillating in plane at right angles to the direction of propagation. The wavelength lambda is the spatial distance between two consecutive peaks in the sinusoidal waveform and is measured in submultiples of meter, usually in nanometers. The maximum length of the vector is called the amplitude. The frequency of the electromagnetic radiation is the number of oscillations made by the wave within the time frame of 1 second. It therefore has the units of 1 second inverse, which equals 1 Hz. The frequency is related to the wavelength via the speed of light c. c equals 2.998 into 10 to the power 8 meter second inverse in vacuum, while nu equals c lambda inverse. A historical parameter in this context is the wave number, which describes the number of completed wave cycles per distance and is typically measured in 1 centimeter inverse. Now, the matter. Given that radiation is an electromagnetic phenomenon, the main feature of matter as far as its interaction with radiation is concerned is the distribution of its electric and magnetic components. From the subatomic scale to the molecular, matter exhibits a variety of electric and magnetic features with which radiation can interact. The figure depicts some of these features for a molecule of ammonia. The forces that hold the molecule together arise from attraction between negatively charged electrons shared between the positively charged nuclei of the nitrogen and hydrogen atoms. The nuclei of each of the hydrogen atoms contain a single charged particle, a proton. The share of electrons between the hydrogen nuclei and the nitrogen nucleus is not equal. Nitrogen commands a larger share. Its nitrogen-hydrogen bond, therefore, has a heterogeneous distribution of charges, resulting overall in a positively charged end towards the hydrogen atom and a negatively charged end. Such a bond is described as having a dipole moment or being polarized. As its nitrogen-hydrogen bond has a similar polarization, there is an additive effect with the result that the entire molecule is polarized or has a dipole moment. Its nucleus of the hydrogen atoms comprises a single positively charged proton. It acts like a small rotating bar magnet or is said to possess magnetic speed. Potentially, the entire ammonia molecule, its bonds, its protons and its electrons all have the necessary prerequisites to interact with radiation. Now, the interaction between radiation and matter. As it has been shown in the previous section that matter can be thought of as possessing many minute electric and magnetic moments on the subatomic and molecular scale. Radiation, which is also electromagnetic in nature, therefore potentially can interact with matter on this scale. If interaction is to be significant, however, there has to be a match between the frequency of the electromagnetic oscillations executed by the radiation and oscillations of the electromagnetic moments within the matter. The situation is analogous to that of pushing a person on a swing. Say, the person on the swing completes a cycle once every second. If the pushes are at some other frequency, then the energy transfer from the pushes is not efficient. The most effective transfer of energy takes place when pushes are in unison with the motion of the swing, that is, with a frequency of 1 per second. The interaction between radiation and matter can lead to the occurrence of a variety of phenomena. Important ones as far as spectroscopy is concerned are absorption, emission, and scattering. Absorption. Absorption occurs when electromagnetic radiation is absorbed by atoms, ions, or molecules within a sample. The basis of absorption spectroscopy is the measurement of the manner in which matter absorbs radiation. An appreciation of absorption can be gained by considering the properties of the lens in a pair of sunglasses. Through the lens, the image of the outside world is duller. Some of the radiation encountering the lens does not pass through. The lens absorbs it. It leads to an increase in internal energy of the chemical species, producing an excited state. This rise in the internal energy is related to various transitions in the atom or molecule under investigation. The specific transition being related to the wavelength of electromagnetic radiation being used. These transitions occur at particular wavelengths depending on the chemical species being studied. This forms the basis of the use of spectroscopy for qualitative purposes. In addition, under particular conditions, the energy absorbed by the chemical species is proportional to the concentration of the absorbing species, allowing quantitative measurements. Now, emission. Emission describes the production of electromagnetic radiation by matter as an excited state returns to the ground state. The chemical species may have been raised to the excited state by absorption of electromagnetic radiation or by chemical reaction. Because emission is the reverse of absorption, the specific wavelength of the electromagnetic radiation observed will depend on the transition occurring. The basis of emission spectroscopy is the measurement of the manner in which matter emits radiation. Now, light absorption and its transmittance. Three processes determine the color of an object or solution: light emission, light reflection, and light transmission or absorption. In light emission, a compound is excited by absorbing energy from a light source. This energy is then released as emitted photons that return the compound to its ground unexcited state. This process is used in flame emission photometry and fluorescence. In light reflection, a non-transparent object absorbs all the wavelengths in the spectrum except for the ones we see. The object reflects the wavelengths that we interpret as color. A black object absorbs all visible light. A white object reflects all visible light. When white polychromatic light passes through a solution, the solution absorbs certain wavelengths and allows the unabsorbed wavelengths to be transmitted. This is called light transmittance or absorption. The color of the substance visible to the eye is the light that is transmitted by the solution. This color is complementary to the absorbed color. The table shows the relationship between solution color, absorbed color, and wavelengths in the visible spectrum. An example of this transmittance is a solution of copper. The copper solution appears blue because it absorbs the complementary color yellow from white light and transmits the remaining blue light. Measurement of this transmitted light is called colorimetry. Now, the importance of electromagnetic radiation in biological science. Electromagnetic radiation has many wide applications in solving many biological problems. The range of electromagnetic spectrum that is utilized for particular measurements defines the technique used. Following are some of the spectroscopic techniques based on the principles of electromagnetic radiation that helps in bringing solution to biological problems. Molecular, ultraviolet and visible absorbance spectroscopy. UV visible absorbance involves electronic transitions, and as many compounds absorb UV or visible light, it is widely applicable in chemical analysis. Liquid and solid phase sample exhibit broad, featureless absorbance peaks, and thus UV visible absorbance is not generally very useful for identification purposes. However, it is very widely used for quantitative measurements. Molecular luminescence spectroscopy. Similar to the UV visible spectrum, the emission spectrum of a substance can be a means of characterizing that substance. Luminescence has the advantage of improved selectivity, as relatively few compounds exhibit fluorescence or phosphorescence, and sensitivity. Atomic absorption and atomic emission spectroscopy. Both of these techniques are widely used for the quantification of metallic elements. Infrared and Raman spectroscopy. Both IR and Raman spectroscopy are used mainly for the qualitative determination of functional groups. X-ray fluorescence spectroscopy. XRF is used mainly for qualitative determination of elements, though some quantification is possible. Nuclear magnetic resonance spectroscopy. NMR is capable of yielding an enormous amount of information regarding molecular structure and therefore unsurpassed specimen discrimination. Furthermore, NMR can be used to analyze a wide range of substances not limited by molecular mass, volatility or polarity. Finally, conclusion. Light is an electromagnetic radiation, a phenomenon exhibiting different energies, and dependent on that energy, different molecular features can be probed. Spectroscopic techniques employ light to interact with matter and thus probe certain features of a sample to learn about its consistency or structure. An understanding of the properties of electromagnetic radiation and its interaction with matter leads to an appreciation of the variety of types of spectra and consequently different spectroscopic techniques and their applications to the solution of biological problems. Thank you.